Thank you. So, yeah, we're all familiar with the exponential decrease of number of people. So by the third lecture, we'll have a cozy audience. And so divide by 2 each time. Oh, well, no, I think it's more like exponential. Selberg's lectures I've seen once took a fantastic record. Okay, so I hope that at least in the first lecture I gave you a flavor of how zeros affect the distribution of primes and other arithmetical objects in a rather profound way. And these lectures, the next 2 lectures, will be primarily concerned, I have this on, with the distribution of the zeros. And I'm going to try to explain in some detail some of the comments that are made in very vague form. And I'm afraid at this point we start to move a little with it. Well, firstly, my style is probably very different to Landau's. I agree, the taste is very similar. But Landau very much was, if you read any of his papers, and this is, some people like it very much, and it's very nice for the reader, he spells everything out, every detail. He leaves nothing to your imagination. In fact, I don't think there are any writers like this anymore. On the other hand, he was interested in things that absolutely are close to what I'm lecturing on. But I will get a little more fancy, I suppose, if you want to call that here, because those are the tools that allow us to go ahead. Now, I'll describe this over the complex numbers, though it's really over the Elliptics that this is used, but you can get the flavor already over the complex numbers. So I want to just describe some aspects of group theory and monodrami groups specifically that are crucial in understanding the function field analog of the conjectures or the statements that I was giving you last time. So monodrami goes back, of course, to last century, where people looked at monodrami groups of differential equations, hypergeometric differential equation, and so on. And they arise in many different contexts. The context here, I'll just take a very simple example, is suppose we have n points, or n minus 1, distinct points in the complex plane. And let's the parameter be the complex plane or the affine line. Remove those points. So that's where my parameter will move. And for each point t, this is all complex numbers, I'll have a curve ct, which I give you in affine form, written like this. It's a hyperelliptic curve. It's y squared equals x minus t into x minus alpha 1 all the way up to x minus alpha n minus 1. These are distinct roots. So as long as t is not one of those roots, which I'm specifically arranging, then I get a curve, a non-singular curve, whose genus we can easily compute. It depends on the parity of n. It's either n minus 1 over 2 or n minus 2 over 2, depending on the parity of n. And it's constant, the genus. And this is a one-parameter family of smooth hyperelliptic curves. However, if t became one of these points, then I would have a double root, and the genus of the curve after you desingularize would change. So that's why we keep away from those points. Okay, so as we move around in the parameter space, we have a family of curves. And there's a monodrami associated with this, depending on various monodrami. There's a monodrami is a representation in some cohomology. In this case, I will look at each one of the curves, affix one of these t0, sorry. I'm not going to move, if you can't see. I think, if that's what you want. Yeah, I think you probably come closer here. I hope you can see. I tried to make these, they're a little more smudgy, but I think they're written harder, so they should be legible, I hope. So I look at the first cohomology of the, I take a base point, t0, I look at the first cohomology there, which you can think of in complex analysis as a holomorphic one forms. And I choose a basis for the holomorphic one forms, and I can, having chosen that basis, and a basis which is holomorphically dependent on t in a little neighborhood of t0, I can study the following problem. What happens if I go around a curve in out my parameter space and come back analytically continuing this basis that I chose at the base point? When I come back, I'll just clearly have a new basis. So in this way, I'll get a matrix. The new basis will be some matrix times the old basis, and that, if you check, does not depend on the homotopy class of this curve, and so you get a representation of the fundamental group of this parameter space, which is just a free group. I assume your n is not 1 or something. That's not a degenerate case. I really do have a serious family here. And so I have this free group here, and I have a representation into linear matrices on this cohomology. And we know the dimension of the space, H1, that's just the genus. However, and this is a very important point, which somehow the Riemann zeta function eventually knows about. I don't know why, because that's one of the missing things in this theory. But in this case, it's clear. We do, if I look at this cohomology, it's dual to homology. And in homology, I have the intersection of cycles is never broken when I move around in this parameter space. So if you think about that for a few minutes, you'll see that in fact you can choose a basis here so that this representation of this free group as it is will be into sp2gz, into that discrete group.
The inclusion is the other way around. It's sp is contained in GL.
Yeah. Thank you. Thank you. Thank you. But it can't be bigger than this. Well, it will always be a symplectic matrix. That's a key thing. And the key thing that I'm pointing out here is how big is this image? It may not be the whole of sp2gz, but it's not too difficult in this example to show that it's Zariski dense in the algebraic group sp2gz. That is, it's big enough that any polynomial which vanishes on the image must already vanish. So it's, in this case, you can even prove its finite index in sp2gz, which is even a stronger statement that you, because this is certainly is a Zariski dense, it's a stronger statement. In the work that I show later, the only notion that exists is Zariski dense, because you're working over the L-adics, so I just emphasize the Zariski density here. And this is proved by computing local monodrami and looking at elements that you get around points, and then verifying these generate a big group. So the important point here is if you have a one parameter family like this, say of hyperelliptic curves, and you look at the monodrami of the parameter space, of pi1 of the parameter space inside H1, transformations on H1, you're going to be big. This is what's saying this family is really moving around in a big as way as possible, but of course there is the constraint that every matrix we get is symplectic. Okay, that'll play a crucial role, and I just wanted to point out this monodrami. And at this point, I have to describe something which will explain many of the comments I made in the first lecture. So now just switch off from monodrami. Monodrami eventually leads to this. We'll be computing scaling limits of monodrami, but for the moment you can just think about pure, if you like, probability theory, and what might really be a chapter that should be added to Weil's book on the classical groups. Just some very simple question that you might ask, and it's as follows. But to set it up, now you might argue immediately, why am I looking at the compact forms of the classical groups? In this finite field, this comes for free because we know the Riemann hypothesis. In the analogous situation which I'm heading to, of course, these things are much more debatable, but I'll explain how they predict answers that we can prove so that there's no question that this is the right tack or the right direction. Here, it's extremely natural. So let G of n, and I only look at classical groups here because I'm interested when the groups, the size of the matrices get big, so any exceptional groups which might appear as monodrami are not going to survive when I make n large. So Gn is one of the classical groups, Un, Sun, SO2n, even odd ones are best to keep separately, and the symplectic, and I write Weil's notation, USP2n. And just so that we all know what we're talking about, USP2n is the set of 2n by 2n matrices, which are both unitary, they're complex matrices, and which preserve the intersection form J. So that's a subgroup of the unitary group, and it's the maximal compact in the symplectic group. So these are the classical families, all realized in the standard way. So I just gave you USP2n, of course, unitary. You're familiar with all of those. Now, there's no parameters in this theory. This theory is going to be a theory about what is the distribution of eigenvalues of a random matrix. So I mentioned here random matrix theory at the top there. That's what I'm trying to understand here. And the treatment here is quite different to the physics text, so I'll make one point of contact there. Right here, there's just no parameters, so it's one's forced just in this direction. A compact group has a unique Haar measure of mass 1, that's a probability measure, and any statement about probabilities that I care to ask will be relative to this Haar measure. Now, given a matrix A, which is unitary, it has eigenvalues. Of course, it can always be conjugated to a diagonal matrix, a unitary matrix, and the eigenvalues I'll write as e to the I theta 1 up to e to the I theta n. And I now do a step which mathematically is a difficult one, but numerically is very easy to do, which is to order the thetas. This is a little bit artificial because they're really periodic, or cyclically order them if you like, around the unit circle. So for each matrix A, I have n numbers, if I'm in Gn, where there would be 2n numbers, around the unit circle. And I want to ask the question how these are distributed when n goes to infinity. And there's a beautiful answer to this. I'd like to explain it. And to explain it, we have to ask what we want to look at. So this is the subject matter, if you like, of random matrix theory. I will look at 3 different measures. The first is just let's look at the consecutive spacings. Some part of this, I actually lectured on this here a year ago, so you're all familiar with it, but I'll review it anyway. I will look at the consecutive spacing, theta j plus 1 minus theta j, and I want to emphasize that I'm looking at the scaled spacings. They're roughly n, or they're exactly n numbers in 0 to pi. So if I multiply by n over 2 pi, I've now renormalized this so that on average these things are roughly of size 1 apart. I would guess we're going to see exactly the truth. So I count how often these consecutive spacings lie in AB, and that defines for me a measure on 0 infinity, which depends on the matrix A. So each matrix A gives me a consecutive spacing measure. And I could, of course, look at the second consecutive spacing, or the kth consecutive spacing, or for that matter, any local spacing statistic. I will concentrate on this particular one. That's a thing which depends on each matrix A. The second thing I want to introduce, because I'm going to try understand in this number theory things which are beyond universal laws, and it is captured by the following, as you will see. I will look at the distribution of the eigenvalue closest to 1 in one of my families, Gn over there. So if Gn is the orthogonal, unitary, or symplectic, let me define a measure on 0 infinity again, which just gives mass AB. The mass it gives to AB is the Haar measure of the set of A's in Gn, for which the smallest eigenvalue, remember I ordered them, divided by n over 2 pi again, this is the natural scaling, lies in AB. So I'm looking at the distribution of the eigenvalue closest to 1, or the theta closest to 0 with proper scaling. So these are just definitions.
Positive closest to 0.
No. Theta 1 was greater than or equal to 0. That's absolutely an important point. I must allow 0. 0 will be eventually the point 1/2. That's the Birch-Swinnerton and Dyer point. I do not naturally eliminate that. Yes, good point. Sorry, it's theta 1 could be 0, and we could ask. And the third, now this looks a little more technical. It's in the end, this is the thing we can prove theorem for.
When you say closest to 1, because it could be
on the one going around counterclockwise. This is a choice right now. Correct.
just one-sided.
One-sided, yes. That's the definition. That's correct. I'm going around counterclockwise. I've chosen a direction. And it could be different if I went the other way. Okay, so the third thing, however, what I define here is the simplest. I'll just call it the density of eigenvalues near 1, scale density, which does not choose the one side or the other side. I write all the eigenvalues, theta j a, and here I will allow even in the infinite set, I write e to the 2 pi I theta j is one of the eigenvalues, and I've chosen any one of the thetas, so I'm adding all, periodizing the whole picture. And what I do is I take a Schwartz function, or think of a function of compact support, I average that phi, but notice I have n over 2 pi. Now I really expect, say phi's compact support, that's going to be roughly bounded, I expect, because I'm multiplying n times the smallest eigenvalue, which should roughly be 1 over n. And then I may have a few other ones which are within 1 over n from their phi's compact support, but eventually that should be really a bounded sum. And certainly if I average it over the group, I will get a density, then that has a good chance to converge as n goes to infinity. So I introduce these three measures. This one is mainly for technical reasons, and the others are completely natural objects, and I ask how do they behave as n tends to infinity. Now this is not an easy question. This is a good part of what Katz and I did in this book, was to understand just this purely simple question of how these behave when n goes to infinity. This is not your usual question in probability theory, because these are not independent variables. If you try to write down any integral here, any probability statement, you have to take the Haar measure and project it down to the diagonal, the maximal torus, or what's called the Weil integration formula, and that gives me a measure on the thetas, which if you ever look at Weil's book or something, you'll see it's got a product of e to the I theta I minus e to the I theta j, very complicated interaction terms. And it's very far from being independent, which is why the answers in the end look very different from what you get if you throw down random numbers on the circle. And that's why the eigenvalues of a random matrix or a random element in a large classical group look very different to random numbers that you threw down on the circle, which we're all familiar with. So I want to emphasize here that the tool that we use is due to a physicist Gordon in the 60s, and I will get back to that just mention. Sorry?
This is called Gordon?
His name's Gordon.
But this is a rigorous...
He had a very ingenious idea, so I'll tell you a little bit about Mr. Gordon. The problem was never studied in this context. The problem was usually studied following Wigner, who was trying to make models of spectra of complicated Hamiltonians, things like, I don't know, uranium, if I remember. And there, what Wigner asked the question is, take n by n symmetric matrices and how the eigenvalues of an n by n random symmetric matrix distributed. So he first put on some measure on the space of n by n matrices, what was called the Gaussian orthogonal ensemble, for example. And then he asked about the spacing distribution. And many people tried to solve this, including Wigner, and he even had a very ingenious guess to the answer, which I'll show you a picture of a little later. But no progress was made until Gordon found a way how to integrate out one variable at a time. Why is it that you can do independent variables? Is if you have a function which depends on the different variables, you can integrate them. But here, if I have a function I want to integrate with this big product of a van der Monde determinant sitting in there, how do I do this integral? And Gordon had the very brilliant idea of using orthogonal polynomials in order to compute these integrals. And that was the breakthrough. After that, a flood of papers came. People were able to make computations. And it also allows us to make computations. So Gordon invented the use of orthogonal polynomials in this. By the way, the interesting thing is the measure that Wigner asks the question. He gets the wrong answer. Gordon proves it. But of course, in the physics literature, this measure is called Wigner's measure. I find that rather strange that the guy, he even conjectured the wrong answer, but when very few physicists know of this work, because Wigner's guess was so accurate that it's good in practice, people use the Wigner guess anyway. I'll show you how accurate it is just now. All right, so we let n go to infinity, and now here's a theorem which tells you the answers to all these questions. The first is, what is so mu1 of a, of course, is a bunch of delta functions. That was the measure of consecutive spacing for a given matrix A. But if I average that over Gn for any of the Gns, now this is why we call it universal. This measure that we get here, if you average and take the limit, there's a unique answer for mu1 or for any local statistic. I'm illustrating it with mu1. This measure that we get here is called in the physics literature the GUE measure. This is what led to all this Hermitian thing with the zeta function. Let's just understand immediately that it doesn't matter which group I started off with, that's why we call this universal. As long as we're in one of these compact classical groups and we take the limit, there's only one answer that it knows to come out with, and I'll show you a picture of it for the consecutive spacing, mu1 universal, which in the physics literature goes by the name of mu1 GUE. And GUE won't be important for us. So that's how the average behaves. But there's a law of large numbers which assures us that the average, the typical guy looks like the average here. In other words, the things concentrate on the mean, which takes some effort to prove. So if I let the d nu mu be the discrepancy between two measures, the maximum deviation they give to any subinterval of the line, interval, so that measures how close the two measures are. In some sense, the Kolmogorov-Smirnov distance between these measures. Then if I average, well, that's a number between 0 and 1, obviously. And if I average that over the group, and I take its deviation of mu1 of a for any a to this universal answer, the limit as n goes to infinity tends to 0. In fact, we get a rate in the proof, but that's not too important. What this immediately says is the typical a will already look like mu1 universal, just by an obvious inequality. Chebyshev's inequality from this. So what happens is not only is the average look like this universal behavior, but almost all start to look like this universal behavior, and we will use this heavily. This law of large numbers is crucial. Okay, so I will show you a picture of what that looks like in a minute. But let me just tell you that the other measures also have limits. So the measure which is the, and as was pointed out, this is the closest to one eigenvalue moving counterclockwise, new one of Gn. It has a limit, a scaling limit, which is now a little more interesting because it depends on G. This, I will show you the pictures of these in a minute. They depend on G, while that thing was universal. So here, if we're doing some theory with something with zeros of zeta functions, we can pick up the symmetry group by recognizing this measure. This measure already distinguishes the different symmetry types G. And most importantly, just look at this for a second. Notice I never gave you any formulas for any of the other expressions. I'll say why in a second. But the density, which is perhaps the crudest of all these statistics, that we can compute this limit. In other words, as this was on the test function phi, this converges to some answer which depends on G, some density against phi of x. And that density we actually compute for each of our families, and they're given by these closed form expressions. And because that's actually a nice simple answer, this will be something that we will be able to tackle in the global case, and it's the reason I'm putting it down here. So just remember that we have explicit formulas. They are distinct for each of these. Let me just remark this, that for the odd orthogonal group, so this is odd SO 2n plus 1, I obviously must have a delta naught, because every matrix of odd, every odd dimensional SO odd has an eigenvalue 1. So there's going to be a delta function, the origin plus some fluctuation. So the density, that's the only guy where there's a persistent eigenvalue at 1. And it's picked up, obviously, with this density. So the nice thing is these are very simple answers. Now, the reason I didn't give you the answers for the other measures is they don't have simple expressions. As I mentioned last time, they're given by some Fredholm determinants or by Payne-Lavez, and one can write down expressions for them that one can use, but it's just, one can also use those expressions to draw them numerically. So, for example, here are 3 curves. Those at the back may not see. There are 3 curves there. The first one, the first one is mu1 classical. That's that universal measure that you take any matrix in a large classical group, any one of the classical groups, and you look at the spacings, normalized spacings between the eigenvalues. Then, according to that law of large numbers, with very high probability, that measure will look like mu1 classical. That's that universal, or mu1, I called it universal. It's quite remarkable that the eigenvalue closest to 0, mu1 symplectic, is within 1% of that. That just happens to be a coincidence that misled us for a long time. There's no reason for it. I can prove they're distinct. There's no reason for it. So it turns out that if you take a big symplectic group and you look at the eigenvalue nearest to 1 in a big symplectic group, and you look at the distribution, it looks very much like that, and most importantly, it repels the origin. Notice these functions vanish to second order at the origin, which means that if there is an eigenvalue, when you're doing the spacings, if there is an eigenvalue, then the next eigenvalue doesn't want to be close. If you had random numbers, the corresponding measure that you would get here, this is entirely elementary, is e to the minus x. The most common, if you put down numbers at random, they like to look like they almost are equal, or there's this large fluctuations. The eigenvalues of a random classic matrix in a classical group are very rigid. Once one comes down, the next one knows not to be close to it. That's the second order vanishing here. And in the symplectic group, that's also true. That's a remarkable fact of life. And I only know how to prove this from computation, meaning computing these answers theoretically, and then the fact that the Taylor series and the expansion here can be done analytically, and you see it. This is the Vignes surmise, by the way. He said he understood that this vanished to second order at the origin, and he also guessed that it behaved like e to the minus s squared times a constant at infinity. So he said, well, perhaps the answer is the simplest probability measure, which has mean 1, because you've normalized it to have mean 1, and has this behavior at 0 and infinity. And then he fits the parameters, and it's within 1% of the truth. What?
Which one's which?
I have another picture. I don't know. I would lie, I can't remember.
For other groups, it doesn't.
Yeah, I'm about to show you. Here's what it looks like for the other groups. So for the orthogonal and the unitary, and the special unitary is the same as the unitary. It's very different. They don't want to keep apart. So if you take a large even orthogonal matrix, take a large SO2n matrix, look at the eigenvalue nearest to 1, it will come near the origin. It will be a bit like random. There will be many eigenvalues very close to 1. While if you're in the symplectic case, you will repel 1. And the unitary similarly. The unitary, of course, you must repel 1 because 1 is it doesn't know about 1. All the other guys know about 1 because there's a symmetry. But a unitary matrix doesn't know that 1 is a special point. So it also shouldn't vanish at the origin. So you can draw these, and that's the nice thing, that you can compute these theoretically, and you can actually draw them. And of course, when you do an experiment, and I tried to say last time that a lot of these beautiful conjectures were first discovered by experimentation, it's important to actually be able to draw the graph. I won't go into how that's done. All right, now I can explain I'm not going to talk about this at all, so I just want to put this graph on there, and I've put it everywhere I lecture, because I think it's a great achievement of a cray, and there are going to be very few crays left as far as I understand from it. Let's go. This is one of the last computations crays do, and they're closing it down. What this is a computation about, let's go. Remember I said something that I called the Montgomery-Odlyzko law, that this is just about the Riemann zeta function. You move vertically higher and higher up. You look at the consecutive spacing between the zeros normalized. This is very important. It's already known by Riemann that the number of zeros between t and t plus 1 is roughly t log t over 2 pi. He doesn't know they're on the line, but he knows by contour integral how many zeros there are approximately there. This means, of course, these zeros have to be 1 over log t apart, roughly. So you do exactly what we were doing in the classical group. You rescale by the total number, so you would rescale them or unfold them, as sometimes it's called, and now you get numbers whose mean is 1, and you look at the distribution of these numbers. And the phenomenological fact that I'm trying to explain somewhat in these lectures is that this is mu1 universal, or what was called mu1 GUE in the literature. I would rather call it mu1 associated with the classical groups, because when we go to the function field, we'll prove this and see where it's coming from, and it's got nothing to do with Hermitian, and it's got nothing to do with anything except that that law was universal for the classical groups. The spacing, the solid curve is what you saw there, mu1 universal. The cumulative are the dots. It fits on the nose, and this is for the zeros, the 10 to the 20th zero in the 70 million neighbors. So that's rather impressive numerical computation and a beautiful fit. And then, of course, what Odlyzko does is he takes any question you might ask about the zeros for which there is a probabilistic answer computed in somewhere in the literature, in the physics literature, and he checks it. And it's so accurate that if you had to ask him or me or anybody who knows this stuff, you generate for me random. In old days, they used to have they used to have tables of random numbers. I suppose we don't have these anymore. Computers have made those obsolete. But suppose I said to you, can you give me a table of random eigenvalues in a big unitary group? Well, it's not easy if you take a 300 by 300 or 400 by 400 matrix and you want to get all its eigenvalues. That's the limit of numerical computation. So if I asked you for 1,000 numbers, you would be stumped perhaps. Well, you wouldn't be stumped. You would email Odlyzko, and he will give you 1,000 consecutive zeros of zeta, and they are an analog. They would be a perfect set of random numbers from. That's how accurate this works. Everything works. Joint, independence. These really are behaving like a random matrix from a classical group is the way I want to view it. And of course, that's trying to tell us something.
But in the classic, in the eigenvalues, you first order the eigenvalues and then you look at the space.
In the random matrix theory, you order them and you also look locally because their density varies. So you have to look where they locally have constant density. Here, we're on the circle. There's no variation in the density. Right? Okay. So I don't want to talk about the Montgomery-Odlyzko law. I want to talk about families. Because that's the behavior in the direction where you vary the function seems to be much richer and much more arithmetic, and in fact has many more applications. This is beautiful stuff, and of course we dream of it telling us something about the zeros, but it doesn't have any particularly striking applications. Well, this I think does. So I want to explain in the next few minutes what the function field analog of this Montgomery-Odlyzko law is, and a little bit how it's proved, and what the source, most importantly, what's causing it, so that when I come back to the Riemann zeta function, we know perhaps what to look for from a different angle. So let me remind you a little bit about function fields. So this idea is in Emil Artin's thesis in 1923. It's one of those great theses that goes by name Artin's thesis. That means it was a good thesis. What his idea was is let's replace the rational numbers by some other field which might have similar arithmetic. And the field he replaces it by rational functions with coefficients in a finite field. So FQ is a field with Q elements. And we replace the rational numbers by that rational function field, and we're going to try make a zeta function, or he made a zeta function. So he takes a finite extension, just like in the rational numbers, or a finite extension of the rational numbers, one forms a zeta function. You start with FQT, you take a finite extension K of FQT. This is how he thought of it, and he formed, just like you do following Dedekind, a zeta function, which is zeta K of T. It's a product over all primes or places as they call it, of 1 minus T to the, we use a variable T rather than Q to the minus S here. It's become customary, so let me stick with that, to the minus 1. So this will be a function of T which converges initially in a little neighborhood of the origin, and then we will see in a moment it's a rational function of T. But he and others quickly realized that this has a, and this we don't have in the number field case, this is already where things diverge in a major way. There's a geometric description of this. So if you choose a curve whose function field is K, so for example, to think concretely, maybe you can realize this, and you can realize this through a plane curve. So this would be a function of 3 variables, a homogeneous function, non-singular. This would give me a plane curve, and its field of functions would be K. So then if you have such a model for this function field, then you might be able to describe the zeta function, and you can, in terms of the geometry of this curve. In fact, as is well known, so if you prefer this definition, you may choose it. You take the following, this following power series, summation n equals 1 to infinity, n t to the n over n, where n is the number of solutions to this equation over the field fq to the n. So we start with fq, then there's a unique extension fq to the n, field with q to n elements, and you count the number of solutions to this equation over that field, and you have a generating function, and that's another way of describing the zeta function. And that opens the way, and this is why we understand much more in this case, that opens the way to studying the zeta function by counting the number of solutions to the equations over finite fields, in particular using Galois theory to use Frobenius. And that's why one knows, if in a nutshell, it's that kind of extra information that's lacking in the other case and that everybody's looking for so desperately that allows one to eventually prove the Riemann hypothesis here. So let me state for you what it is. Already Schmidt in 1930 remarked that the Riemann-Roch theorem on this curve, so you're doing this now over finite fields, but that is easily developed, allows you to write the zeta function as a polynomial divided by 1 minus t, 1 minus qt. So there are 2 poles, just like with the Riemann zeta function. This is already in symmetric form. And there's a polynomial of degree twice the genus of that curve. And it's got integer coefficients, which this is really the beef of all the zeta functions. So the zeta function is a polynomial. Ignore this. This is elementary. And the zeros of that polynomial are what the Riemann hypothesis in this case is all about. There's a simple functional equation, which is that t can be replaced by 1 over qt, and that thing remains invariant, and that's proved by the Riemann-Roch. And the Riemann hypothesis was a central problem soon after this, for this model, or this case, and it was proved by Weil in 1941, during the war. Actually, if you read his biography, he admits he didn't have a proof. It's interesting. He says he was in jail somewhere, and there was one lemma he couldn't prove, and he was worried he wasn't going to get it through the war, and he actually smuggled out a thing that was communicated in a contrandu note, but there was a lemma that he didn't know how to prove, and he could only prove it in 1945. So I put there a little question mark. I don't know whether you want to consider it proved in 1941 or 45, but he understood that when he had time to concentrate, that wasn't really going to hold him back. He gave 2 very different proofs, and they both are extremely important. Anyway, the result is that the zeros all lie on the circle of a fixed modulus. And it's extremely useful in and of itself. Not just I'm viewing it here as an analogy of the Riemann zeta functions, but this particular theorem in the theory of exponential sums, there was just a conference on that. This is the heart of all that subject. This is how Klostermann sums got to be evaluated with a correct size, and these are extremely useful when you're doing any kind of number theory. So this was a major advance. Now, let's give ourselves the Riemann hypothesis. This is why we can go much further. And let's ask about the distribution of the zeros in this function field case. We know so much more. Maybe the Montgomery-Odlyzko law is really there for a reason. So just like I did when I had a matrix with eigenvalues from a classical group on the unit circle, I formed the consecutive spacing measure. I can form the consecutive spacing measure between the zeros of this zeta function. So for each curve, I have a zeta function. Then I have the zeros that are all on the circle. I form this consecutive spacing measure, or I form any of those other invariants that are statistical quantities that are discussed for the classical groups. And to make contact with the first thing I was discussing, or one of the things I was discussing last time, and to show you, somebody asked, did the genus go to infinity? Yes, the genus will be forced instantly to go to infinity. That's the only analog of the question. That has to be the case, because let me remind you what was a family. I'm driving at some family that I am fascinated with, and that's the family of Dirichlet L functions, Ls chi with chi squared equals 1. This is a family of L functions which I'm trying to call a family. Now let's look at the function field. If you think about Ls chi, it's very easy to see that if you know a little bit, if you multiply the Riemann zeta function times Ls chi here, you will get the zeta function of a quadratic extension of the rational numbers. So what this family really is one common factor, the zeta function. And if I'm looking at low-lying zeros, I made a big deal that the smallest zero of the Riemann zeta function was very high. So the lowest zero of a quadratic extension will be coming from this L function, not from the Riemann zeta function when I multiply them. So I'm really looking at all quadratic extensions of Q and their zeta functions and looking at the distribution of zeros. Well, in the function field, then that's clear what I should be doing. I should take K equals FQT and look at all quadratic extensions. How do I get quadratic extensions? Well, I'll look at any delta which is a polynomial which is monic and square free with coefficients FQ and degree n. I'll call those HNFQ. And then I will adjoin the square root. So I'm looking at the curve. In the curve language, this is y squared equals delta x. So that question we were asking about quadratic, about Ls chi, chi quadratic, in the function field is exactly the family of all hyperelliptic curves over FQ. They naturally jump at us. And I will stick to that. This is not the only family I just highlighted in the beginning with hyperelliptic curve. Everything can be done in generality, but this is as good an example as any. In fact, I think better. So here's, if I want to look at all the quadratic extensions of FQT, I'm immediately forced to choose delta to have higher and higher degree, which means the genus is going to go to infinity. And ask about the distribution of the spacings or whatever. And now I can state the theorem we prove in the function field, which I said is the Montgomery-Odlyzko law, and where it comes from. So this entire slide is going to mean here that what I will call from now on SP infinity symmetry. So I was using symbols completely undefined last time, and now they hopefully will get some meaning. The moral is that we're going to have some monodramies in the function field, which will be have some parameter, which is like the genus going to infinity for hyperelliptics, and the monodramies will have been computed, they're SP2G, and when I put SP infinity, it would mean that I've let G go to infinity. Okay, that's this picture, and the exact theorem we prove is that the typical curve in these hyperelliptic families, the typical curve, so I look at all quadratic extensions of FQT, the typical curve, not all, the typical curve will have its spacings follow this fantastic rule that Montgomery and Odlyzko were pointing, or Odlyzko was finding numerically, the Riemann zeta function obeys. So let me read it to you and explain the notation. So H and FQ are all the polynomials, monic polynomials of degree n, which are square free. And that's a finite set, so 1 over the number, the sum over these polynomials, mu k, mu1, I only defined mu1, sorry. Mu1 of the curve over fq means the measure that you associate with a consecutive spacing measure for the zeros of the zeta function of that curve. And I look at its discrepancy to the universal answer predicted by the theory of random matrix theory. And the claim is that if I take 1 over the number, the sum over all of them of the discrepancy, this will tend to 0. And there's a cheat. Somebody at the end of last lecture, immediately he'd been at this conference where this has been a weakness, and it is a weakness in many of the tools in the subject, is I really wouldn't like to have that q go to infinity there. I have been setting up an analogy so that I started with the rational numbers are replaced by fqt. I didn't say I was going to vary q, but the techniques we use here are such that if we fixed q, we know nothing. So there's an extra limit here, and that is a weakness. And it's a very serious weakness, but I believe it's true for any. Oh, yeah. Yes. But I don't have evidence for that. This numerically, we have no idea how even to experiment with something like this. But right now, this kind of thing is very difficult, and the Q here allows you to go ahead and see symmetry and how monodramy plays a role, but if Q is fixed, we don't prove anything. So that's a weakness. And notice it's in this order. Let me be entirely honest here. And the low-lying zeros, they follow. Now this, of course, doesn't pick up the symmetry. All this in the hyperelliptic family, and I started out with monodramy, everything was symplectic. That's because of this intersection form. Everything was symplectic. But this law of large numbers that I described there, which of course is used in the proof here, says that the spacing between the zeros never picks up the symmetry type. It's washed out in this universality. So this doesn't say anything about symplectic. This is mu1 universal. But if I look at the zeros near 1, after, on the circle radius 1 over square root q, and I look at the zeros counterclockwise near 1, yes, in this case you do prove that the low-lying zeros converge to the measure nu1 or nu k, symplectic. The symplectic is different. I drew graphs of these, so it really does pick up already the symplectic symmetry. And the density is this density WSPX, of which I gave you the formula. So all these theorems come out in the function field, and that's the sense in which in the function field we have established what that law is, and for families what the low-lying zeros are. Just a word about the proof. Get the function field behind us here. So of course the proof, as I've been hinting, very much depends on the fact that for the family of hyperelliptics, which is what I was describing there of genus G, this monodramy is the full symplectic group. If it were something close to the full symplectic group, you probably wouldn't have any problem proving this as well. But if this group, this monodramy group, were much, much smaller, then the answer would start to change. So in this function field, it's not that we can almost always answer the question as long as we are able to A, compute what the monodramy of the underlying family is, and B, compute the scaling limit of the monodramy. That's a highly non-trivial step to actually determine the scaling limit. So it's not that we can always do it as far as we can tell at this point. A very important ingredient is Equidistribution Theorem, which allows you to pass from this family of zeta functions whose zeros are associated with conjugacy classes of Frobenius and an equidistribution of Frobenius. All these, I mean, that's how one can proceed here. And underlying all that is a very important paper of Deligne, Weil 2, in which he proves the general Weil conjectures, which are used in the proof. And of course, this probability theory at the beginning is what's at the heart of the scaling limit. So I would say in the function field, we see where this is coming from. It's coming from the fact that this family of hyperelliptics has a certain group, a symmetry group, and that's the reason that the distribution is as it is, and we in particular do pick up this remarkable feature, this universal distribution that the zeta function has been found phenomenologically to obey. Okay. Now, I want to end with the function field, and the next 10 minutes and the next lecture are entirely devoted to the number field, where, of course, things are never at the same satisfactory state, like we don't know the Riemann hypothesis. Yet, we can go very far, and this really was a pleasant surprise to me. We can, firstly, predict things rather remarkably, and we can prove a tremendous amount towards us. So there seems to be the symmetry group in this case too for a family. So I'm going to go back to the first lecture, and I want to talk about families, and I'll only give you 3 examples, and let me be clear here. I only have 7 examples right now in total. Our theory consists thus far of 7 examples, meaning I would love to say that for any family of L functions, there is like a Galois group that you associate with a family, and it tells you what the distribution of low-lying zeros is. But I must confess that I don't even have a definition of a family. So it's right now it's still a theory that I hope, but the examples we have are rich and beautiful, so I don't feel we have to make too many excuses here. The first example is the one that's this hyperelliptic family. It's a set LS chi squared equals 1, of which I was just talking about the function field analog. So this is the set of Dirichlet L functions, all quadratic extensions, which is the most abelian thing that anybody knows. Quadratic extensions are abelian, but we are saying now that somehow they behave like these hyperelliptic with larger and larger genus, that they somehow glue together with some symmetry which is SP infinity. The second family, which is very interesting, and we are not as advanced about it as yet, but I think we will be soon enough, is the set of all LSE where E are the elliptic curves. So you go over all elliptic curves over Q, you look at their L functions. Those are modular, as I said, by Wiles. I should have said also Wiles and Taylor. Taylor's contribution is crucial. So LSE, this is a very beautiful family, and it's got a lot more surprises, I think, hidden in it. And maybe in a year I would be able to tell you, or somebody would be. I'm sure somebody else will also. Somebody might be able to tell you a lot more about that. But anyway, the 2 I'll talk about are 1 and 3 mainly. LSF, where F were for these modular curves, x naught n, the set of all holomorphic forms of weight 2 for gamma naught n, of which there are roughly n of them, the genus of the curve, and these are Hecker eigenforms, and n goes to infinity. In all these cases, I will now sort of give you the general setup. The analog of the genus go to infinity, or the analog of looking at all quadratic extensions, is to allow the conductor to get large. And we look at the distribution of the low-lying zeros. So this is a way of thinking of this. So in each case, I mean, this could be done in great generality for L functions of modular forms, but it's safe to say that most of the action still happens in the upper half plane. It's amazing how rich this upper half plane is still for us without having to go to GLN or anything like that, even though in the end to understand these, I think the other groups are indispensable. So I concentrate on GL1 and GL2. So LSF, the L function of a modular form in the upper half plane of the type there, it has a conductor. So every L function in the world has something which tells you how complicated it is. For Dirichlet L function, it's that period Q. So the Riemann zeta function is the simplest of all of them, and its 0 is way unusually high. As soon as you increase the conductor, the zeros start to trickle down to a half. And we're looking at distribution, how they come to a half, and is specifically how many are at a half. So LS chi with C chi equal Q, that's the conductor in that case. For an elliptic curve, the conductor is what is defined as the conductor of the elliptic curve, which is by looking at the elliptic curve where it's got bad reduction and with specific recipes. So it's the same as that conductor. Incidentally, I don't know where the word conductor comes from. Okay, I'm not sure why it's used, but it is used by everybody. And for the LSF, where F is a modular form, new form on gamma naught n, where n is prime, let's say, as I was mentioning in the last lecture, the conductor is simply the integer n. Okay, so there is this parameter, and the theory is such that it fits very nicely with the following. That I will look at the zeros of any of these L functions. They're all supposed to satisfy the Riemann hypothesis, etc. They have Euler products. And for this lecture, I'm going to, for the next 10 minutes, assume the Riemann hypothesis. The next lecture will be entirely devoted to removing that and proving entirely unconditional theorems. But to move ahead with something as hard as this, let me assume this, if you don't mind. And I would be happy to prove the conjectures of Brummer or whatever, even assuming the Riemann hypothesis. So let's proceed. So we write the zeros as a half plus I gamma fj, if I order them up and down the line. And the gammas are real, so I can order them. Particularly, I might look at the lowest zero, which was like the 0 near 1 in the function field case. And what's nice is in all cases the correct object to look at is to take gamma f1 times the log of the conductor over 2 pi. That's the correct scaling. So this conductor is so important that it actually tells you how to rescale that low zero so that when you move, you'll be moving roughly a bounded amount. I mean, the number that you should see, how should I say, that's a correct rescaling. And the proof that it's a correct rescaling is the theorems that come out and the numerics. So I now vary over this set of L functions in my family with conductor less than x. This will always be a finite set. And I ask how these low-lying zeros behave. So how can I approach this? Well, I firstly can form the function field analog, which usually means a call to Katz, and he'll call me back with a monodrami. Then we'll compute out the scaling limit if possible, and we'll know what to expect. So that's a strange way to proceed, but it is the one way we can come up with answers. It hasn't failed us. In every case, it's given the right answer. And sometimes this is quite subtle. The function field predicts something a little strange, and sure enough, it comes up in this case. So that's sort of at the back here. And this is really pushing this function field analog to the limit. When I was at Stanford and there were fewer algebraists around, I always thought, this function field, this is the toy problem. It'll never really say anything of any seriousness for the Riemann zeta function. And it's still, people have looked and it hasn't quite done anything that you can really say has changed the zeta function. But yet here it's predicting questions that I would never have guessed that if I looked at the Richler L function with character chi-squared, that the spacing distribution is governed by SP infinity. So the function field seems to be at least a fantastic predictor, and at the end of next lecture I'll try indicate what might be the cause of that. But right now it does predict answers. In particular, it predicts the density. If I understood the density, I would understand everything that of the type that I described in the first lecture. So let nfx be the number of functions, L functions in any of these examples that we might have in mind whose conductor is less than x. And let's average, remember this log conductor over 2 pi is the correct scaling, an arbitrary test function, 1 over the number, the sum over all the L functions of conductor less than x, sum over all zeros, that's a density sum. And we can ask whether that converges to the phi against the density predicted by the function field. That's something that's very concrete, and I will call it the density conjecture, and one can try to prove that directly. So in the function field, of course, we have a group acting on a space. We have a symmetry, and it's used in the proof. In this case, we don't have a cohomological interpretation of the zeros. We don't have a Frobenius. Nevertheless, things are predicted which we can try prove. And that's our procedure. Everything that I've said there, which has been checked numerically by Rubinstein by actually increasing the conductor of Dirichlet L functions or of elliptic curves or of twists of Ramanujan, all GL2 stuff with bigger and bigger conductor has checked out on the nose. So it's like initially with Birchman and Dyer, people just check numerically different examples and always fit it. That seems to be working here. In other words, you can predict the distribution and different kind of questions, and they're not always the same answer. These answers change from family to family, and the data changes from family to family exactly according to the prediction. But one can prove, and I want to describe some results of that type. So I'll describe 2 such results that you can prove in applications, and these are assuming the Riemann hypothesis for any L function that might come my way. So I form the density sum for the simplest of the cases. This is the Dirichlet L function whose lowest zero, I'm now telling you numerically, follows the symplectic. I should say something here, even at a purely phenomenological level, this explains something that was a mystery for many years. If you take these L functions and you look at the lowest zero. Now, when computers came in, I said Birch and Swinnett and Dyer came up with this conjecture. There was another set of people around Turing who started computing the zeros of the Riemann zeta function higher and higher. Of course, with the hope of finding a zero off the line, and then you can be famous, but in a strange way. Well, it'd certainly be interesting. And they went higher and higher, and people would write papers which would say, yes, there are no zeros off the line between here and here and here. But Odlyzko changed that into a science when he started to use what he computed to try to learn something from it. But there was a man by the name of Hazelgrove who thought, quite reasonably. Perhaps if it's false for an L function, and then I don't have to go high. It may be false already, like a Ziegel zero on the real axis. So he started varying Q long before Rubinstein. He didn't go as far as Rubinstein, obviously, but computed the lowest zero, in fact. And he found a phenomena which is known as the Hazel-Grove phenomena, purely experimental observation, that if you have these quadratic characters, not cubic, quadratic, that the lowest zero doesn't want to be near half. It repels a half. He just said this in words. There was no sort of thing to even measure this by. But of course, that is that distribution I drew. Nu 1 symplectic vanishes to second order at the origin, this Fredholm determinant. And of course, Rubinstein, when he's checking this numerically, finds this repulsion and is exactly following that law. So that Hazel-Grove phenomenon is beautifully explained by this symplectic symmetry. And this already starts to prove this in a very dramatic way. So the theorem is that this theorem, the densities are what they should be, and if you look at the symplectic density, it vanishes to second order also at the origin. And this is proven, but of course, unfortunately, not for all phi, which would be the entire conjecture, but for phi whose Fourier transform, this is a Schwartz function, is supported between -2 and 2. I'll say this interval -2 and 2 is extremely important. I would, of course, the whole philosophy says this is true with no restriction like this, but the fact that we can get that far is already remarkable. You're right. Stanford Qual problem, favorite. Unless phi is 0. You can't have phi and phi out of compact support. Yeah. Okay, so a much tougher result, and which uses the techniques that I'll describe next time, which involve unconditional results as well. Here we're assuming Riemann, is if you look at gamma naught n, this x naught n and the L functions of weight 2, so as to understand this Jacobian. And then, of course, you break them up into even and odd, as I described in the first lecture. The functional equation, half of them have even and half of them have odd. And if you do the same thing, you form the density, and I decide whether to look at the even and the odd separately, because then I'll get different densities here. And in this case, the function field prediction, if I didn't describe that here, I only described these hyperelliptics, but one can make a function field analog here, and the prediction is an orthogonal symmetry, so all the distributions are supposed to look very different, and indeed they do, provably. And again, we get this for all phi, where the Fourier transform is supported in -2, 2. And this is very pleasing that, firstly, we get the right answer. This is a theorem, modulo the Riemann hypothesis. This is a theorem. We get the right answer. And moreover, I wanted to emphasize this region -2, 2. Because this is the first time, now this is a little technical, but you could, I'm sure, imagine what I have in mind here. So, of course, these should hold without any restriction whatsoever. But that the range -2, 2 is so important is the following. Everything is eventually proved with the Fourier transform of that density, because the theorem somehow indicated that that's going to happen since the condition was on the Fourier transform. And there's something about the Fourier transform, if you take any of those functions, and the Fourier transform is defined with e to the 2 pi I, incidentally, so that's what made -2, 2. If you compute the Fourier transform of those functions, 1 minus sine 2 pi x, those list of elementary functions that were written down, they all have the property that they are discontinuous at plus and minus 1. Now, all results previous to this on pair correlation in the vertical direction, which are similar kind of theorems, which I haven't described at all, never went beyond the diagonal. The fact that there's this discontinuity is a big hint, and it's a crucial pointer to the fact that you're not going to just get the answer from squaring and diagonal, but there are going to be new terms that come. The answer is supposed to change here, and you're supposed to pick this up from your analysis. I'll show you next time a little bit where it comes from. And this is the first time where we get non-diagonal terms contributing to this, and when they come and contribute the exact right function, it is very pleasing. It makes you really believe that you have penetrated this conjecture quite deeply. But that's a matter of, that's a matter of everybody can evaluate for themselves. So the conjecture is certainly true in this range. But in this case, we have, of course, applications. For example, I want to get back to arithmetic applications, which is the theme of the first lecture. This will, in particular, if I knew that conjecture for any phi, I will know how often I vanish at a half. if I only know it for this restricted set of fees, I already can make an estimate for how often it vanishes a half. So I can make an approximation to that. And so if you just do that in a clever way, you get the following application. And I want to point out this is better than what I wrote down on the first lecture. If you look at this big quotient, which has got finitely many rational points, which are called the Morel quotient, this is just using this with this range. This range minus 2, 2, I was emphasizing, is important because that point is minus 1, 1. I'll be finished in a second. So that I went past that discontinuity. Now this all uses heavily the fact that we've gone to the more than the diagonal. Then the Brummer conjecture, whatever I mentioned last time from those tables, would be that this should be asymptotic to that with a constant 1. I mentioned that Ivanic and I proved entirely unconditionally that that's greater than or equal to 1/2 times that. And now you have a number slightly bigger than a half. And I said that if we got beyond a half there, we would have no Ziegel zero, which is why we're desperately looking there. So you say, wait a minute, yeah, you got bigger than a half. Yes, but I'm assuming the Riemann hypothesis here. And if you assume the Riemann hypothesis, of course there are no Ziegel zeros by definition. A Ziegel zero is a zero very close to 1 or a very bad violation of L1 chi being small. So this, of course, when I start assuming the Riemann hypothesis, forget the Ziegel zero. You've assumed it doesn't exist. And that's why one got beyond a half here without having conquered the Ziegel zero. But this uses these results in the group, and you get 9/16. And I end with just a statement about the rank. This is, again, assuming the Riemann hypothesis and the Birchman and Dyer conjectures. The rank, I haven't defined it, but it's just simply the number of generators the group of rational points on this Jacobian is a finitely generated group. That's Bayes' theorem in this case, I suppose, for abelian variety. The number of generators, the rank of this finitely generated abelian group is that number. I was only talking about rank 0 in the first lecture. One can try and understand what the rank of J naught n is. So if we assume all the conjectures we have now, of course, the conjectures that the symmetry has, the O infinity, would imply that the rank is asymptotic to J, the dimension over 2. The approximation we have here gives us, that's trivial, bigger than that, and we get below 1, which uses a full non-diagonal, and 1 was sort of a demarcation line we wanted to get beyond. Not that I know any magic thing that I can use that for, but it's getting closer to a half. All right, so next time I will describe how you do these, what's at the heart of any of these kind of theorems in families, in particular how you attack things unconditionally, in particular the use of Klosterman sums. Any questions?
Why this very last line, rank less or equal dimension is not being form of this?
Like this?
No, the other side.
Yeah, this is obvious.
No, but the other side, if you set up the 99 over 100, you had just rank less or equal dimension. Is there any better explanation for the rank less or equal dimension?
Why is this hard to prove?
No, with 99 over 100, do you mean that without the 99 over 100, just rank less or equal to dimension?
It's much easier, but it's not trivial.
It's not trivial at all. But it was not known yet.
Oh, nothing either. Right. After this, using the method that Ivanic and I, there are now some beautiful results of Michel and Van der Kamp and Kowalski on this, which are entirely unconditional, which I will explain next time.
The novelty is not in the 99 over 100 so much.
Right. That's not the novelty, but I would say that if you work in some sort of obvious direction, you'll get to 1 with some ease, and if you really want to go beyond 1, you really have to understand beyond the diagonal. So it's more like a technical achievement. I wish I had a long, deep application of just getting that, like we do in the case of the real question. There's much more. Any other questions?
I ask you about the fact that you're using hyperelliptic curves here. Does that take anything away from it, or would you have it?
It's just, I think, the family that one should. It's got all the characters, all the depth, and if you understand that, you really understand the most general case. So there's no reason to look at others really, other than to check your theory. If you have a theory which says, look, you've discovered a Galois of the problem, then you want to have different examples with different symmetry groups and seeing then that the numerics and the theory give these different answers. So the main reason we looked at these other ones, which was not hyperelliptic families, was to test the theory, and secretly also to look at a case where we would have arithmetic applications. Because the theory of the low-lying zero is the extension of the theory of when you vanish a half. And so obviously, given today's world with Birchman and Dyer, you run to those examples for that purpose.
So it's not like the case, for example, de Vries equation versus the KP equation, where you use hyperelliptic curves as the first.
No. When you want to, so the theorem actually, the book is not stated by it. So already, of course, stated for the moduli of all curves. But the way you prove the monodrami is large for your general curve is to, you can't compute general things. As long as you have small families for which it's large, and for the bigger family it's even larger. So the hyperelliptic is, in fact, the one parameter hyperelliptic is the basic computational device. But when we prove the Montgomery or Lutzow law for the function field, we say, well, why do we look at hyperelliptic? We, in fact, stated the theorem for your generic curve over FQ, and we look at the moduli space of, in fact, all curves do it. But I don't see any difference, as long as your family is big.
Any further questions? Thank you very much.